Good morning, everyone. This is 9 a.m. in Hong Kong. So good morning from Hong Kong and good evening to Professor Maurer from Canada. Welcome everyone to this distinguished lecture by Professor Maurer. This lecture is jointly hosted by the Research Center for Sharp Vision and School of Optometry of the Hong Kong Polytechnic University. My name is Chia Su Ki, the moderator of today's distinguished lecture on how the baby learns to see critical periods revisited. This lecture will last for about 1 hour and followed by 30 minutes of Q&A session. To ensure a smooth and pleasing experience throughout the session for all participants across the nations, please kindly turn off your speaker and you may type your question in the chat box and I will read your question in sequence towards the end of this lecture. This lecture will start after my introduction to Professor Maurer's outstanding career achievement in neuroscience research. Let me start now. Professor Maurer is a distinguished university professor from McMaster University, Canada. Although officially retired, she continues to do fundamental research on how perception develops. She has over 200 peer-reviewed publications and many awards. These include the Donald O. Hebb Distinguished Contribution Award of the Canadian Society for Brain, Behaviour, and Cognitive Science, and she is also being elected a Fellow of the Royal Society of Canada, the American Association for the Advancement of Science, and the Association of Psychological Science. Beyond her academic research, she is active in setting Canadian national policy on the ethics of research with humans. Please join me to welcome Professor Maurer. I'm going to pass the time to Professor Maurer now.
Thank you so much for that generous introduction, and thank you to all of those being here fairly early in your morning. It's late in my evening in Toronto, but I'm really pleased to be here. Let me start sharing my screen. Does everybody see that? Everything okay?
Yes, everything is okay.
Okay. So newborns can see, but their vision is very poor. It takes all the way until adolescence for vision to become as precise as it is in adults. We're going to talk about what happens when a baby is born with cataracts in both eyes that prevent them from seeing for the first few months after birth. What happens to that visual development? And in the patients we studied, the cataracts were so dense and central that they blocked all patterned vision to the retina. Treatment involves removing the cataract's lens and fitting the child with a compensatory optical correction. In our studies, a contact lens. So here's the logic of what I'm going to show you. This is one of our patients, Carl. He was born with cataracts in both eyes, so there's no pattern visual input. He had surgery. In his case, it was at 3 months. In the population, it can vary from 1 week to 11 months. And then the patients came back to the eye clinic where the eye was healed and received the corrective contact lenses 1 to 3 weeks later. And when I talk about the duration of deprivation, I mean the time from birth until they finally got those contact lenses and could see focused input for the first time. Usually that was between 2 and 6 months of age, but it could be as early as 2 weeks of age or as late as 11 months. And then I'm going to tell you about what happened to their visual perception measured when they were adult. So they've had years and years and years of nearly normal visual input after treatment with which to fine-tune the system and to recover from any initial deficits. So saying the same thing in pictures now, They had a cataract, they had surgery, they had contact lens fitting, and then we have Carl here, who's going to have years and years of visual input and will measure his visual perception when he's adult. And whenever you see an image of Carl in the corner of my slide, that means I'm talking about patients treated for bilateral congenital cataract. We've studied maybe 20 aspects of visual development in this population, and only 4 of them were spared. That is, only 4 of them turned out to be normal once the patients had grown up. All of them, interestingly, are present at birth. That's key because it means they developed, at least in rudimentary form, in the womb without any visual experience. So maybe it's not surprising that they can be refined as well, missing that first visual experience. So let's start with color vision. Now, if I were going to test your color vision, you might be able to tell those 4 squares up there apart because the yellow looks the brightest, the green is the dullest, and you could tell these are 4 distinct shades of gray, discriminate between them, and be completely colorblind. So to find out about color vision at birth, we had to overcome this confound of luminance. And here's how we did it. We essentially bored babies with looking at gray squares. We used a habituation technique. So we showed this young lady a gray square. She was very, very interested, looked for a long time. And then we showed her a different gray, still interested. And then still another gray and another gray. And she told us in many ways that she was getting bored with looking at gray squares. But at this point, she's seen 5 different luminances of gray. We called her habituated when the looking time went down by at least 50%. And then we gave her a test. This is a 6th gray luminance. She remains bored. And then we switched to a colored square. She told us in many ways that she could discriminate gray from green. Our measure was whether she looked longer at the green square than the gray square. And when we used this technique with newborns, we found they can discriminate the primary color, these primary colors, yellow, red, or green from gray squares. So there's some color vision at birth, lots of refinement after birth. Now, to test color vision in the adults, we can use standard techniques you probably use in the clinic yourselves. So we tested them with the Farnsworth D15. With this test, there are colored chips. They're in scrambled order. The subject has to put them in order so that neighboring chips are most similar to each other. People who are color deficient make errors, that's shown here, the errors in color deficient. They don't get the ordering right. They have things that are, this green might be over there. And they have confusions as shown here. So they might have one of the purple ones over among the blues. When we gave the Farnsworth D15 to the adult patients like Carl, treated for congenital cataract, they were just like controls. A perfect score is 11. Most of them were perfect, just like the controls. A perfect score on confusions is 1, and most of them had that perfect score. We also gave them a harder test. It's called the Lanthony New Color Test. It's like the D15, except you have 4 different levels of saturation, including one that's pretty tough because the chips are fairly desaturated. And the cataract patients were normal on that test as well. So color vision is preserved despite early visual deprivation. Same for shape discrimination. To test shape discrimination in newborns, we use the same technique. We bored them with looking at a shape like a triangle and then showed them a square. Ah, they said, that's something new and different, or they said it by looking longer. And we showed them faces that had different eyes in them. And again, they showed us they could discriminate. When we gave a hard shape discrimination test to the patients like Carl treated for bilateral congenital cataract, we asked them to sort all of these shapes into either the triangle pile or the square pile. So you see what we're doing here is we've got squares of different sizes. We've got a luminance change. We've got occluding bars. We've got a triangle where the angles are much more acute, and the patients were perfect on this test. So they seem to be able to process shape into categories and discriminate among shapes. And when we asked them to discriminate between two faces or a whole bunch of faces, then the difference was just in the shape of the eyes and the shape of the mouth, but we've kind of put them in the same place in every face. Again, they were as accurate as controls. So shape discrimination is also preserved after early visual deprivation. The same for biological motion. Biological motion refers to the fact that if you see point lights on the joints of an adult and you watch that person, those point lights moving, just from the pattern of movement, you can tell that that's an adult moving over to the right, probably male, I would say around 30 years old. You get a lot of information about biological organisms just from the patterns of movement, and that is called biological motion. Now, to test this in newborns, Francesca Simeon was worried because they probably had seen the mom moving around and the dad moving around, so they weren't totally naive to human movement, so she used chicken movement. Now here, those black squares are located where the white point lights were shown to the baby. Okay, and let's look at what happened to them. This is a chicken moving, or in a control condition, these are just random squares moving, or this is an upside down chicken moving. So what the newborns were looking at, and they were 1 to 4 days old, this is the sequence that they saw. The chicken moving, remember they're white dots, they're not these black squares, random movement, or upside down chicken movement. And the question was, would they prefer the biological chicken to random motion? So it's a choice between two things. So chance is 50%. Yes, they'd rather look at the moving chicken pattern than at random motion. And they'd rather look at it right side up than upside down. So already at birth, there's sensitivity to biological motion. And to test this in the cataract patients like Carl, we did something very like the chicken test. We had normal biological motion. Again, I put the black circles where the white point lights would be. We had the same patterns of movement, but we just scrambled the phase. So everything was happening out of sync. So the arms were moving out of sync with the legs, etc. And then to make it really hard, remember these are adults, so we have to make it really hard, we added noise dots. So we had random dots doing things on the screen, and we asked, how much noise can you tolerate and still tell whether you're looking at the scrambled one or the normal one? And the patients were completely normal. They could tolerate 70 noise dots on top. Let me just go back. They added noise, we could put 70 noise dots on top, and they could still tell whether it was biological motion or not, just like the normal controls. The final thing that we found that's normal after early visual deprivation is face detection. Now this one's tricky for newborns because newborns don't see very well. And when I'm talking about newborns, I'm going to use this icon over here of our newborn looking at the colored squares. So this is a simulation from Van Hofsten of mother's face. This is a picture of mother's face as we would view it when viewed from 30 centimeters. So guess what? You can't see very much of it. You can see there's an outline, you can see there's some hair, and a little bit about the internal features, not much. Move it back to 60 centimeters, not much is visible at all. And 120 centimeters, it becomes a ghost. So how much information can a newborn pick up from a face? Despite that limitation, if you show these very simplified drawings, so we have here a paddle, it's kind of head-shaped. We put 2 black squares in the location of the eyes, another black square in the location of the mouth. Versus, we invert those so it doesn't look at all like a face. This one looks more face-like to us, and newborns look at it longer. They'll turn their head to follow this one, and they'll look at it longer. So they have a preference for a basic face-like structure. You can get this in babies. We got it in babies that were just 10 minutes old, by the way. So barely have any face experience. And you can get the same thing even in the fetus. If you put laser beams on the mom's tummy and you put them in this pattern, the fetus will turn towards it versus this pattern, which don't turn towards. So this doesn't require any visual experience. But it's hardly an innate face module, because if you use these two, a T and an inverted T, you get exactly the same preference. You get a preference, the one that has more stuff going on at the top. If you take a face and you scramble it, but one version has more energy at the top, and the other one, you put the energy down at the more energy down at the bottom, the newborn prefers this one. There seems to be a general preference to look at something that's contained and has more energy at the top. And if you match that, so now look at these two. This is obviously a regular human face. This one is all scrambled, but they're matched more or less on how much energy is at the top. Newborns don't care. These are equally good for a newborn. So there is a preference that draws babies to faces. It's sufficient to keep the baby staring at the mom's face, which the baby quickly learns to recognize, but it's a very crude face preference. Now, if we switch to the patients, and they're grown up, so we can give them a much harder test, we use Mooney faces like these. What you do in a Mooney face is you take every pixel and you turn it to black or white. And what that does is it removes the edges defining the features, but it keeps a kind of basic configuration of the face. Or you can do the same thing with scrambled faces. So you can probably tell that this one over on the right, that looks kind of like a face. This one doesn't at all. And so the task we gave the subjects was to look at a whole bunch of these and in each case make a judgment. Is it a face or is it scrambled? And here's what we found. So here is accuracy. Patients are in white, the controls are in black. Very high accuracy, just as good as controls, and they're just as fast. These are reaction times on correct trials, and the patients are just as fast as controls. So we have these 4 things that, despite early deprivation, are normal once the patients grow up. Either they were completely spared or they were able to recover by those years and years of postnatal visual experience. And that leads me to posit this kind of developmental framework. The baby comes biologically prepared. There are certain things that the baby can already do at birth before any visual experience. We talked about color, shape, biological motion, and face detection. Then there's lots of refinement postnatally, and I'll show you that refinement depends on visual experience until we finally have the adult with a very specialized visual system. But before I go on, I have to tell you this recovery of face detection is not quite complete in the patients. We brought them back and did event-related potentials. So we put EEG electrodes all over the head and recorded their brain waves as they did the same task, judging whether on each trial we were showing them a face or a scrambled image. And when you do this with controls, so what you're seeing here is the brain wave from the time the stimulus came on, that's at 0. This is on the left, this is over the right hemisphere. These are over occipital electrodes, these are over parietal electrodes. Scrambled faces are in red, the Mooney faces are in black. So there's an initial wave around 100 milliseconds without differentiating between the Mooney faces and the scrambled faces. But then there's a negative wave, it occurs about 170 milliseconds. So it's called the N170, and it is larger for faces than it is for scrambled faces. Now, if you look at the patients, you'll see exactly the same pattern. There's a P100 that doesn't differentiate. And then there is something around 170 milliseconds, which is larger for faces than it is for scrambled faces. But there's a big difference between the patients and the controls. These waves are huge. Look at the amplitude of the P1, compare the controls to the patients. Look at the amplitude of the N170. So if the patients have normal performance, but what's going on in the brain is different. They seem to be recruiting additional neural resources in order to get that level of accuracy. And in fact, here I'm showing you the amount of amplification that we found as a function of the duration of deprivation after birth in days. So this is less than 2 months, this is out around 7 months. And the longer the deprivation lasted, the greater that amplification, seemingly the more neural resources needed to be used in order to get that level of accuracy. So yeah, face detection is not affected, but its neural underpinnings are abnormal. And perhaps not surprisingly, if we ask the patients to do harder face tests, so if we ask them to discriminate between Jane and her sisters that I'm showing you here, they look like 5 different individuals. What we've done is take Jane and then move the location of her eyes and the location of her mouth. Everything, all the shapes are the same. It's just the configuration we've changed. And if you're an adult with normal vision, that's easy for you. You can tell those are 5 different people, at least if they're upright. If I turn them upside down, I bet they all look the same to you. We have become expert at doing this with upright faces. And here's what happens with the patients. When we ask them to make same different judgments, so we should play 2 of the Jane sisters right in a row, and we do it pretty fast, it's hard, even the controls aren't at 100%, the patients are worse. And they're also slower. So their reaction time on these correct trials, it takes them longer to make any kind of accurate decision. So they can't judge facial identity quite normally. And if we ask them to recognize famous people, so now we're getting into kind of more everyday perception. You see someone, you're supposed to figure out who it is. If you know them, we had a famous faces task. We did not use Carrie Lam. We used people that these patients in Ontario would recognize, and they told us they were people they would recognize. They're not as accurate as controls. And in fact, in this whole battery of tests on facial identity, they're as bad as people with prosopagnosia. So I've told you the baby is biologically prepared, but then there's input necessary. Some of that input that's necessary is right after birth, because if it's missing, you're never going to get to be normal on discriminating facial identity. We've looked at all of these aspects of vision, and they're all abnormal in patients treated for bilateral congenital cataract. Acuity, binocular vision, peripheral vision, contrast sensitivity, sensitivity to slow rates of flicker, sensitivity to global form, and sensitivity to the direction of motion. And I'm going to tell you some of the details about acuity and sensitivity direction of motion. So here's where we're going to start. You know the history. They have visual deprivation. They're treated. They're wearing contact lenses. And now we're going to look longitudinally. We're going to study their acuity longitudinally from the moment they could first see as they grow up. We're going to track what happens. Now, when they're treated, they might be 3 months old, so we can't actually use a letter chart. That will not work. So instead, we used what are called teller acuity cards. So this takes advantage of the fact that babies have a preference for stripes, anything patterned, in fact, over plain gray. And you show the stripes sometimes over here on the left, sometimes over here on the right. And when the baby can see them, you get an eye movement in that direction, which this observer behind here is looking through a little peephole and watching a baby's eye movements. In all trials, the stripes are made smaller and smaller until the baby starts to respond randomly. And that presumably is at the point where to the baby, the stripes can't be resolved. And it just looks like gray on the left and gray on the right, and you get random performance. When you use teller acuity cards with normally developing children, it takes out to about age 7 for them to get to a value as good as in adults. Here's my 7-year-old. So I'm showing you the best acuity achieved with tiny stripes towards the top, large stripes towards the bottom. This is the size of the stripe on the retina in minutes of arc. So if you're an adult with normal vision, your acuity is a little bit better than 1 minute of arc. So you're way up here, like this normal 7-year-old. Newborns can see, but look at this. They're down here around 40 minutes, more than 40 times worse than 7-year-olds and normal adults. There's rapid development over the first 6 months, and then very, very, very slow progress out to 7 years. So what happens when these kids treated for cataract can first see? All of their values were within this circle. We tested them within 10 minutes of their getting the contact lenses, thanks to a tremendously cooperative ophthalmologist. They had had deprivation as short as a week to as long as 9 months. Yet all of the values were like those right here of normal newborns. In other words, acuity had not progressed in the absence of visual input. To put it another way, this rapid development in children with normal eyes is being driven by visual experience. However, the system had not been dormant because they rapidly start to catch, whoops, went the wrong way. They rapidly start to catch up. Sorry, there we go. they rapidly start to catch up. So by the time they get to the first birthday, almost every single one of them is within normal limits. Hurrah, the ophthalmologist said, we treated them early enough. Vision has recovered. Our program is a success. That was premature because we continued to follow the children longitudinally. And when they got to be about 2 years of age, they hit an asymptote. They stopped improving. So their vision at 2 was normal. At 3 was falling behind, at 4 was still farther behind, and it stayed behind because that was their level of vision when they reached 18 years of age. So we have a sleeper effect here. Sorry, I don't know why this is going the wrong way. Probably I'm hitting the wrong button. Okay, we have a sleeper effect here. Something that happens back here prevents the system from improving further once the child is 2 years old. This changed the brain in a way that's not manifest in the child till the child gets to be 2 years of age. Sorry, I don't understand what is happening with this button. All right, let's go on. We also were able to study children who started off with perfectly normal eyes. They had normal eyes from 6 months to as late as 15 years of age. Then they had exactly the same treatment. They developed cataracts. They had a period of visual deprivation. They had surgery to remove the cataracts, got contact lenses, and we measured their acuity with a letter chart when they were adults. I'm going to show you the results in a kind of cartoon format. So what I'm showing you is acuity measured when they're adults with a letter chart. This is going to be when the deprivation started, and this is a normal value. So I've already shown you that if it starts at birth, the final acuity is way down. There is a huge deficit. If it starts at 3 years, there's a deficit, but it's smaller. If it starts at 7 years, there's still a deficit, but it is still smaller. In other words, throughout the first 7 years of life, when children with normal eyes develop normal acuity at 7 years, visual input is building those connections. If you are missing visual input anytime during those 7 years, you will not develop normal acuity. And these are seemingly permanent deficits. And if you develop a cataract between 7 and 10 years of age, you also show a permanent deficit. So that tells us that between 7, you've got all the connections you need for adult-like acuity at age 7, but you need to have input to strengthen them. If you have a period of visual deprivation, you will end up with a seemingly permanent deficit. We were also able to study children who were treated for unilateral cataract. This is Natalia. She's going to be my icon when I'm showing you images of the results for unilateral cataract. And I'll always be talking about vision in the previously deprived eye. In unilateral cases, the treatment is identical, except for the addition of patching of the good eye to encourage usage of the previously deprived eye. So Eileen Birch did a study where she looked at grading acuity. So small values are down here, big stripes are up there. Here's a normal developmental curve showing you going down to almost adult levels by 6 years of age. When treatment was very, very early and patching had occurred 90% of the waking time at the start, 50% of the time in parvovirus, all with good compliance, These patients do as well as the bilateral patients I've already told you about. So look, at the beginning, they're worse. They're like newborns. They normalize and then they stabilize at a level that is not normal. Now, when the treatment is not quite so early, the plateau is much worse. They never get to quite the same level, even if they're good patchers. You see an earlier plateau. And if there's not good compliance with patching, this is now from our sample, you already see a drop off at 12 months of age. So here's the bilateral group I already told you about. These are normal values at 12 months. The bilateral patients have normalized. They have normal acuity at 12 months. The unilateral patients who are good patchers also have normal acuity at 12 months, but those who are poor patchers are already showing huge deficits at 12 months of age. And that pattern plays through to the end. So this is the final acuity measured on a letter chart in our unilateral sample. So this is the final acuity. It's in log units, so normal is right there, where I have the red dotted line. Worse and worse acuity is as you read up. This is the amount of patching, hours per day, for the first 5 years of life. And the more patching there was, the better the final acuity. Nobody's normal. You don't come out of normal with this condition. But if there's very little patching, the final acuity is much worse. And this supports a general principle. We've also learned this from animal work, that vision is worse after monocular deprivation unless there was extensive patching of the non-deprived eye. So, yes, vision is refined by input, but it's also perturbed by imbalances. I've told you about the imbalance between the eyes. Let's look at sensitivity to the direction of motion now. So you are all sensitive to the global direction of motion. If you're looking at a flock of birds and you can't see their faces, you will see the wings flapping, and there are all kinds of local directions of motion, but you can integrate that and get a sense of the overall flow. Or if I'm waving my arms and my legs and I'm walking, even though I'm Italian, which I'm not, let's suppose I'm Italian and I'm doing all this local stuff, you'll still be able to tell the direction in which I'm moving. Now in the lab, we test this with what's called random dot kinematograms. So here I've taken a whole bunch of dots. Each one lives for a very short time, but during its lifetime, they always move up. So you have no difficulty telling that the global direction of motion is up. And we say that's 100% coherence because they all move in the same direction. I can make it a little bit harder by having half of them move in random directions. You can probably still see that the global direction is up. In fact, adults are very good at this. In the lab, we can get the coherence down to 8, 9, 10%, and you can still figure out what it is. 90% of dots are moving in random directions. You can still figure out what the 10% are doing. So before I show you the results from the patients, just let me tell you, newborns don't see direction of motion at all. We develop sensitivity to direction of motion beginning 2 to 4 months of age. And it takes us a full 12 years to become as sensitive as adults. So let's think about that for a minute. We're talking about patients. They missed early visual input, and a lot of the time out they had was during a period when the baby with normal eyes isn't sensitive to the direction of motion. So you might think it wouldn't matter. You're wrong, but here we go. So now we're going to look at their motion processing when they're adults. So we got their coherence thresholds with those random dot kinematograms. Here's our normal control group that came in with a mean around 8%. 92% of the dots could be going in random directions, and they could still figure out what the 8% were doing. The bilateral patients deprived from birth could do the task, but they're terrible at it. They need almost half the dots to be moving coherently in order to figure out what that direction is. And the patients where the deprivation started postnatally from as early as 8 months were completely normal. These are the same patients I just finished telling you have abnormal acuity. You know, I showed you onset at age 3 years, 7 years, 10 years. They all have abnormal acuity, perfectly normal. They are perfectly normal at seeing the direction of motion. So I gave you this cartoon as the picture of the critical period for damage for acuity when you need visual input. We're going to do a similar cartoon for motion. It's got to look something like this. Yeah, birth input is really important. During that initial period when the baby with normal eyes isn't very sensitive to the direction of motion, you need to be getting visual input. It takes to age 12 to get adult sensitivity, but you can take huge time out in this period of time and still have perfectly normal global motion when you grow up. We also tested unilateral patients like Natalia, and here's another surprise. So here's our normal group, 8%, our patients up over 40%, the bilateral patients up over 40%. The unilateral patients, they're not quite normal. But look at that, they're doing much, much better than the bilateral patients. So this general principle doesn't work once you get to higher level visual processing, like the direction of global motion. So let's review. We've talked about acuity, which develops over 7 years. We've talked about sensitivity to global motion, which develops over 12 years. Both are severely affected by early binocular deprivation, but they have very different critical periods during which they're damaged. Acuity all the way out past the 7 years of normal development. Global motion, the critical period is over before the first birthday. General lesson, if you know the period of normal development, you don't know anything about the critical period for damage. It has to actually be studied. The other thing I've told you is that for acuity, there's kind of the expected pattern. The deficits are worse after unilateral deprivation than after bilateral deprivation. You can try to counteract that by very early treatment and very extensive patching. But you really have to work hard. It's usually the outcome is worse. But then when we got to global motion, it was a reversal. The unilateral patients are not normal, but their deficits are much smaller. So one thing for sure, this general principle is not general. So what's going on here? And the hypothesis we've been exploring is that maybe there's cross-modal reorganization going on that affects the unilateral and bilateral patients differently. This kind of hypothesis came out of a literature on the congenital blind. So these are individuals who grow up never having any visual input, period. And when you ask them to do tactile tasks, like read Braille or make tactile discriminations, something very interesting happens. So you have an fMRI recording while they're doing the task. Here is a side view of the head. The nose is here. This is the back of the head. The visual cortex is back here. So in the control, there's a lot of activity up here in somatosensory areas. Nothing's going on in visual areas while this tactile task is going on. Here's someone blind from birth. Again, there's activity in somatosensory areas, but look at this, all of that activity back there in the occipital cortex that was seen only in the blind. Here's something similar when blind are asked to decode auditory motion. So imagine the sound of footsteps, and they can be moving, the sound can be moving to the left or moving to the right. And your job is to decode the direction of motion. In the blind, but not the sighted, there's activity in visual areas again. So this this is a slice right through the brain. So the nose is now up here. This is the back of the brain. The crosshairs are on V1, V2, where there's a lot of activity in the blind. And this is V3 and V5, the visual motion processing areas now being used for auditory motion in the blind. So I wondered, in the patients treated with cataracts in both eyes, who start off like the blind, could this rewiring of visual areas to do other things have already started before they get treated? And maybe they can't get all of those visual neurons back for vision after treatment. That was our hypothesis. And if you are a unilateral case and you always have had normal input into one eye, maybe that's sufficient to keep those areas visual. So you still have them to work with after treatment. So that's a hypothesis we've been working on, and let me show you what we found so far. So now we have the same cohort. We're going to look at their cross-metal processing when they're adults. We're going to see if they can see with their ears. So we did a study in the scanner first with the bilateral patients, very similar to the one that was done with the blind I already showed you. So we had footsteps going to the right or going to the left. We also had someone speaking vowels. And the subjects had to tell us when we occasionally increase the duration of a trial. So whenever they heard that something was longer, they had to push a button. And the patients and controls were equally accurate. So they are paying attention equally well. And here's what we found. This is an inflated brain. So you have to think about taking a brain and blowing it up with air so that all of the fissures are more visible. The front of the head is up here. This is the back of the head. These are visual areas. And in the cataract patients, but not the controls, there was activity back here. It's in the cuneus. It's sort of V3-ish. It's a middle visual area that does respond to visual motion. So there has been some rewiring in the patients treated for bilateral congenital cataract to use visual areas to process sound. And those areas, that extra wiring might be functional because we found that they're faster to detect sound. So in this study, a light came on or a beep, and the job was just push this button as soon as you hear it. You know, it's just a reaction time task. These are correct reaction times. Patients are in black, controls are in white. No difference for the flashes, but when it was a beep, patients are much, much faster to detect the sound. That's a really big difference in reaction time there. Bridget Ruder's group did another study where the task was to detect the direction of motion. What way are the footsteps going? And in the hardest condition, the patients are significantly more accurate than the controls, so they can hear the details of sound better. And in a fascinating experiment she did, that's kind I wish I had thought of, She adapted the patients to an auditory looming stimulus. So imagine that you're in the lab and I'm going, boom, 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 boom. So you are hearing the sound of a looming object, but you're only hearing the sound. And then I show you looming squares. Okay, so you've gotten a looming auditory stimulus, and now I'm giving you looming squares. About 80% of the patients had a visual after effect. So adapted hearing, you get visual adaptation. A few of the controls reported it too, but it was very weak. These effects in the patients were much stronger. So there's some intermixture of the auditory and visual processing in the patients treated for bilateral congenital cataract that is not seen in the controls. And we and Richard Werder's lab have done other tests showing that audition is different in the patients treated for bilateral congenital cataract. So we do find increased seeing with the ears, as I put it here, increased cross-modal confusions and interactions in the patients. And we speculate there may be less of that in the unilateral patients because those higher visual areas were getting visual input from the fellow eye all their lives. And our data to date shows that they don't see with their ears. They don't show the kinds of effects that I've been telling you about supporting this hypothesis. So I already said that this period of refinement by visual input is perturbed by imbalances between the eyes. It's also perturbed by imbalances between the different sensory systems. And finally, we end up with a specialized system. So we commonly assume it's too late to fix things. Traditionally, it was assumed it's too late to treat amblyopia successfully in adulthood. That has been challenged lately, including by Ben Thompson, who's at the PolyU Optometry department. So we asked the question, can we teach new tricks to these, well, they're not old dogs, to these adult patients? So here's what we're going to look at now. Can you rescue these systems when these patients are adults? So they have this early history. We have documented scads of visual deficits when they're adult. Is there any way to rescue them? So we did a study with 6 adults, all treated for bilateral congenital cataracts. The deprivation had been up to 10 months long. They were at least 19 years old, and their final acuity in their better eye ranged from 20/32 to 20/100. So what did we do? We played a first-person shooter game with them. We played Medal of Honor with them. Why? Well, it's known to improve vision in normal controls. It's also what I would build into a therapy. It's vision for action. You have to monitor the whole visual field. It's extremely motivating. You have to act in order not to be killed. It's titrated to the performance level, so it remains possible but challenging. It's known to increase dopamine levels. It has a lot going for it. So they came into the lab. We did a complete psychophysical workup. They played the game for 40 hours, 10 hours a week for 4 weeks, and we monitored their playing, so we know they did this. And then they came back for another weekend of psychophysical testing. I'll show you the results for acuity and global motion. So this is functional acuity. We measured it binocularly, everyday vision. We measured it with a letter chart. So 20/20 or 6/6 values are down here. The initials refer to individual patients. This one's actually Carl. So there are 6 individual patients, and this is the mean. The red symbols are from before the 40 hours of training, and the black is from after. And 5 of the 6 patients showed improved acuity, 1 didn't change, and that shows up in the mean. And we had them back 9 months later, and these improvements stick, which you would expect, because now they can see better. They see better every single day. So this better vision gets practiced all of the time. Here are the results for global motion. So they're all abnormal before to very abnormal. The others are a little bit better. Normal is around 10% or better. And 4 of the 6 improved, and that's shown in the mean, and that improvement also stuck. But again, if you can see motion better, you use that in everyday life. So we were not surprised. Overall, we found improvements in acuity, sensitivity to motion, contrast sensitivity, face perception. Now that's interesting because Medal of Honor does not require doing anything with faces, and yet their perception of upright faces improved. No improvement, of course, for inverted faces, and sensitivity to slow rates of flicker. There was no improvement in stereopsis. There was no improvement in peripheral vision. But this was a 40-hour intervention in a lifetime. There's no reason to think that we have hit the limits of what could be achieved. So even though the system has depended on input to become specialized, it remains malleable in adulthood. I want to acknowledge my many collaborators. The cataract work, in particular, Terry Lewis was involved in every study I told you about. And these are other people who have been involved in collecting the data. The ophthalmologists at the Hospital for Sick Children who made it possible to test acuity 10 minutes after baby first got contact lenses. And of course, the many funding sources that made it possible to do the research. I thank you very much, and I'm happy to answer questions.
Thank you, Professor Maurer. It's a very wonderful talk summarizing very details of the advanced research in baby vision and the impact of this early deprivation on the later visual development. So the session is now open for Q&A. And during your talk, the first question came already at 9:28, about 28 minutes after your talk. So let me just read it out. So the question is, since the aphakic eyes fitted with contact lenses, even if optically adequate, have no refocusing, how then can you isolate the neural suppression from time of deprivation and the lack of focus? So that's the question.
That is an excellent question. I've said that after the patients got the contact lens, they had nearly normal visual input. But of course, as the 75% of the audience in optometry will be well aware, that's going to be a fixed focus. The natural lens has been removed from the eye. The contact lens gives them a single focus. They do go into bifocal glasses before they enter school, but still it's not completely normal visual input. So in each of the studies, we have run controls to evaluate that hypothesis. And in every single case, we have been able to rule it out as the sole reason for the deficits. It may contribute, but it's not the sole reason. And probably the most convincing data come from Ron Booth's work with monkeys. He created aphakic monkeys on the day they were born. So he created monkeys who had no ability to focus. And then he gives them a contact lens and he sees what happens. And they end up with very, very small deficits. But when he simulated a cataract, in addition, the deficits were much larger. So the principal amblyogenic agent is going to be the initial deprivation. but there may be a contribution from the continuing milder deprivation from not being able to accommodate to different distances.
Thank you. So the second question, is it possible to measure the coherent motion sensitivity in young kids or infants? That's more as a methodological question.
We've measured sensitivity to coherent motion in children as young as 5. We can make child-friendly versions of the tasks and get 5-year-olds through it. With babies and toddlers, it would be very difficult to get enough trials to get a threshold, because what you have to do is test a whole bunch of different coherence levels. So you could get it out of a group. So if your question is not clinical, but basic, and you want to know what's the coherence threshold for 2-year-olds, you could test 2-year-olds in a whole bunch of different conditions, but probably each child wouldn't do them all. And you could find out that at age 2, here's the coherence threshold. But if you have a clinical interest and you want to know if sensitivity to global motion is normal in this 2-year-old sitting in your clinic, I think it would be very difficult to do that. I can help you come up with a task that will take 30 minutes to do it with a 5-year-old. Then, you know, more attentive 4-year-olds, probably more likely girls than boys, at least in Canada, would sit still and go through it, but not younger than that.
Thank you. Nick, the third question, would you share the difficulties when conducting experiments on infants and young children, and how did you overcome them?
It's challenging. So first you have to recruit them. So you have to find a source of information on who's had babies who might be willing to bring them in. You have to explain to the parents what you will do and reassure them. And many of them are just as curious as we are to find things out. Even with, when I said 10-minute-old babies prefer that more face-like drawing, we actually did that in delivery suite. We had recruited those parents while they were still pregnant. And we got paged when the mom went into labor and went to the hospital. The most challenging thing with testing vision in infants and toddlers is sleep. They sleep a lot and they get into a circadian rhythm and they'll sleep for 4 hours at a time. So then the challenge is convincing the mother to stay until the baby wakes up. You know, if you have tea and a pleasant environment, sometimes they will. If you have child-friendly tasks, usually, and they're not too long, usually crying and fretting and, you know, a stressed out baby is not a problem. Now, some of these measures, people are doing very clever things with evoked potentials. So they have all the electrodes in a swimming cap, so they can rapidly put them on a baby's head, you know, press them down and try to get neural markers of some of these aspects of visual perception. And it's possible you could actually use that to try to get coherence thresholds from babies. You know, you wouldn't be getting behavioral indicator, but you might be able to get some kind of neural signal that's differentiating moving stimuli from coherently moving stimuli from randomly moving stimuli, and might be able to do it that way. But the most challenging thing is sleep.
Okay, gotcha. Thanks. So the next question is more about the critical period. So as the global motion matures in 8 months old and acuity matures in 7-year-old, is there any evidence that the development of M pathway is earlier than P pathway?
Oh, that's a really tricky question. Now, let me just rephrase it a bit. It's the critical period to damage acuity goes out to 10, and the critical period to damage global motion goes out to 8 months. Sensitivity to global motion develops over the first 12 years. It's just a critical period to damage it by visual deprivation that ends around 8 months. That's a really controversial topic because what marker are you going to use? And what level of the nervous system are you talking about? Are you talking about parvocellular versus magnocellular layers in the LGN? Are you talking about inputs to V1? Do you really mean dorsal versus ventral stream? Where the dorsal stream has more magnocellular input and parvocellular stream has ventral stream has more parvocellular input, but there's so much interaction already when you get to V1 and more interaction as you go. It's very hard to know how to answer that question. However, I can say that our data, like a lot of developmental data, support what's called a dorsal vulnerability. That is that things that depend more on the dorsal pathway are more easily damaged than things that depend more on the ventral pathway. And we've seen that in our data because we saw huge deficits in sensitivity to global motion after early bilateral deprivation. We did a logically equivalent task on global form. So now we have a ventral task. I'm showing you bunches of dots that can look like a swirl pattern because every pair of dots is forming a swirl. And then I can make a bunch of them random and ask you, is this the swirl or is this the random one? And you can get a threshold for sensitivity for global form. There are deficits. They are larger in bilateral patients than in unilateral patients, but overall they are much smaller. So global form is less impacted by early visual deprivation than global motion. In other words, what requires the ventral pathway is more damaged by early visual deprivation than what requires the ventral pathway.
Right, thanks. That's a very detailed explanation. So the next question is the shape discrimination test related to age and intellectual development? And if there is any difficulty when conducting these tests to the children?
We screened intellectual disabilities out of our cataract sample because we didn't want deficits to be attributed to cognitive problems. So in our sample, we can't answer that question. However, the form test, the shape test I talked about, we've used it as young as 3, just in a normal control sample. And I'm sure you could go to 2. Kids love sorting. If you watch a toddler, they sort spontaneously. And that's what we're asking them to do, sort these into 2 piles. And I'm sure you could do it as young as age 2. And I'm sure you could do it with someone who's intellectually challenged.
Mm-hmm. All right, thanks. So the next question is about the tests that you have done for the children. So any comments on depth perception within this critical period in monocular and binocular deprivation?
Depth perception?
Depth perception, yes.
They seem not to have binocular vision. So they don't seem to even fuse. So on the Worth 4 dot, where you're showing a number of colored dots, the person's wearing red and green filters, and some of the dots are red, some are white. And the question is, if you fuse them, you'll see 4. If you suppress one eye, you'll see either 3 or 2. If you have double vision, you'll see 5. The bilateral patients typically see 5. The unilateral patients typically suppress, they see 3 or 2. Sometimes the bilateral patients have developed a better eye and a worse eye, and they'll also see 3 or 2, but we don't get fusion. And if you test them on a traditional stereopsis test, like the RANDOT, they can't do anything. However, we are suspicious that there might be some what we're calling hidden binocularity in some of the patients, and that if we use a test that's adapted specifically to them, it's a bit easier. We're exploring this right at the moment. Ben Thompson is part of this group. We're studying this adult cohort, and we're looking to see if we can find any sign of binocularity in them. And we're also looking at their visual motor behavior. You might wonder, how does vision get integrated with the motor system? So a first-person shooter game, they could do it and improve their vision. Did their visual motor behavior develop normally? Our pilot data says no, not at all. There are going to be huge deficits in visual motor behavior, but we're exploring that as well.
Thanks. So the next question is, any nutritional strategies for improving baby vision in these critical periods?
Interesting question. I don't know. I'd be interested to hear if someone in the audience has an answer to that one.
Not sure if there is any nutrition specialist here.
Well, there is work. They changed babies' formulas because it was found that if you didn't have, oh my goodness, long chain poly acids in the formula, which are normally found in breast milk, there was a problem in acuity, and there could be possible retinal damage. Eileen Birch did that work, and the composition of baby's formula has been changed as a result. So yeah, nutrition matters. We know that's been shown in that case.
All right, thank you. So the next question, I believe you have covered this, but I just want to make sure that I'm not misinterpreting this. So she asks, you mentioned after 40 years of training, there's an improvement in the visual acuity of adults. So she wants to ask, has the improvement been maintained after some time, say after 1 year or so?
We retested at 9 months and it had been maintained, which, as I indicated, was no surprise to us because these are visual abilities we've improved that are used in everyday life. So in a sense, there's ongoing training. If you can see smaller print, you read smaller print. You're decoding global motion all the time in everyday life. If you see it better, you will use that skill that we have developed.
Well, so far, that's all the questions in the chat room. I would like to take the liberty to ask questions as well. So from many of your slides, I saw a common theme that when you're trying to present the idea of improvement in the vision due to some treatment, you use the word of imbalance challenge. So my question is, so you presented the data for binocular deprivation as well as monocular deprivation. So for imbalance challenge, it seems like it only occurred in the second case, but not in the first case with, I mean, bilateral deprivation. There is no competition between the two eyes. So my question is really the effects of this deprivation, is it due to bilateral competition or is it due to something more than that?
Well, there has to be an effect of just the pure deprivation because we see all those deficits in the bilateral patients. And that's also true in the animal literature, where there are deficits when you impose binocular deprivation by having an opaque contact lens or by shutting one eyelid, shutting both eyelids, you see deficits. So you add the competition in the unilateral case. Now, I think I know where you're coming from. So the bilateral patients have the problem of competition between senses. And the unilateral patients have the problem of competition between eyes.
Right.
So in each case, there's something interfering with normal visual development. I think, to go back, the bilateral patients, where they come out surprisingly badly, and not because they're doing worse than the unilateral patients, those are our higher level vision. And in the congenitally blind, the rewiring is for higher level visual areas. You get very little of it for V1 or V2, is higher visual areas. So I think the deficits we're seeing in low level vision after bilateral deprivation probably are pure effects of deprivation. So the deficits in acuity, which I showed you, I didn't show you, but there are deficits in contrast sensitivity, there are deficits in peripheral vision, those low level visual functions that depend upon input from the macula all the way up to V1. Those deficits are probably not from imbalance, but just from pure deprivation. They're worse in unilateral cases because you also had competition. Now, when we go to higher level vision, where there are many brain regions involved, there's a lot of integration. There's integration across eyes. There's integration across spatial frequency. There's a lot of feedback. That's where the competition between sensory modalities can interfere with the recovery that's possible after treatment.
All right.
But I told you it was a working hypothesis.
Yes.
You know, so just put a little maybe in your mind beside that.
All right. Thank you. So may I have my last question, since there is no question in the chat room still. So my last question is more on the strategies of how did you pick those visual tasks to test whether they have recovered or not. I think this is related to one of the questions as well from the audience. One task that I have come across is orientation sensitivity, and it is not tested or included in the list of your recovery visual tests. So I'm just curious, because it is amazing to me that they are already born with all that 4 categories of visual acuity or visual performance, and what is the logic behind of you choosing these 4 and probably not others? That's my question.
Okay, we didn't choose the 4 that were not affected. We chose 20.
Okay.
And those were the 4 that turned out to be okay.
I see. Okay.
They're not where we started. We have done orientation sensitivity and normal development. So newborns are sensitive to changes in orientation, big ones. Orientation sensitivity gets better with age. We haven't tested it in the patients. Trying to think if another lab has done that. Does not come immediately to mind. I mean, I predict it's going to be abnormal because it's low level vision, acuity, contrast sensitivity are abnormal. I suspect orientation discrimination at threshold. They'll be able to do it. At threshold, I predict will be abnormal, but we haven't done it.
Well, as far as I know, I was in Ron Howard that lab for a while. So at that time, I think Yuzo Chino also did an experiment to do this single cell recording from the cortex about whether this orientation sensitivity already occur at birth. And the answer is yes, it is. So I was wondering whether this is also one of the, inborn or innate visual behavior.
That's interesting. Although in the animal models, in the cat animal model, I think that orientation selectivity of cells after monocular deprivation is not normal.
Mm-hmm.
So let's just say, I don't know.
Thanks. So apparently there is one last question. So this is the very last, hopefully. As the visual impaired patient was shown to shift the visual cortical cells to facilitate the auditory function, will this also happen in myopic patients? So this is probably from the from one of us. Will these changes vary in myopes with different severity? Oh, so it's more on this special population affected by short-sightedness.
I predict no. I predict, okay, so you're talking about bilateral high myopes. I suspect that that is nevertheless not severe enough to cause the cosmodal rewiring. It's a good question. I mean, it's something that one could look at. So their vision is still probably going to be better than the newborns, even with bilateral high myopia. They will never have been without any pattern visual input. So if we think about the visual areas at the back of the brain, particularly V1, V2, when one eye is stimulated in a spot, neighboring spots are also stimulated, and the other eye is stimulated. So the input, the same pattern of input, comes from multiple neurons at the same time, 2B1. When the auditory system is stimulated, yeah, there are weak connections in the normal newborn from the primary auditory cortex to the visual cortex. But the auditory cortex is tuned to auditory frequency. And that means there's going to be scattered input to the visual cortex. So if you've got this coordinated barrage of input from the eyes or this scattered input to the ears, the eyes are going to win out, even though it's not very well focused. And maybe the baby doesn't pay very good attention. Vision is still going to be primary. It's going to be the stronger input. And as long as you have a stronger input, those weak connections from somatosensory cortex, from the auditory cortex, are not going to get strengthened. They're not going to take over. That's my prediction.
Okay, thanks a lot. So I guess that's all the questions from the chat room. And I think this concludes today's lecture. And I want to thank Professor Maurer a lot for this excellent talks, bringing us to the current knowledge of how baby sees, and as well as answering all these questions patiently. And I think we have very stimulating answer as well to follow up on that. So with that, I want to thank you. And I want to end the session now.
Thank you so much for inviting me. It's been my great pleasure. And thank you all for coming. Feel free to email me if you have additional questions.
Thanks, Professor Maurer. Goodbye now.